Once again, welcome all for this introduction to ferrous alloys. Inside this, we have started the brief classification of metals. Myself, Dr. S.G. Kulkarni from Sinhagad Institute, Mechanical Engineering Department. So, during last lecture, we have seen that the broadly metals are classified into groups ferrous and non-ferrous alloys. Then, in ferrous metals, iron is the main content, and in ferrous alloys, by considering carbon as well as by alloy, low carbon steels, medium carbon steels, high carbon steels are the classification criteria for the ferrous alloys. Then we have seen the brief classification of ferrous metals, inside that as steel and cast iron. Inside the steel, so before going to steel, we have started the cast iron, and inside this grey cast iron, inside that we have seen the grey cast iron is formed upon slow cooling and silicon rich cast iron, and it is characterized by occurrence of graphite flakes. Also we have seen the ductile cast iron is made when magnesium or cerium is added and annealing process is carried. Okay. So in cast iron, grey cast iron and ductile cast iron, that part we have studied. Coming to white cast iron. So from this white cast iron, we will continue this lecture. So white cast iron contains less than 1% silicon, which results in more residual cementite. So as name suggests, cementite, it increases the hardness and ductility decreases. So in white cast iron, less than 1% silicon is present. It is a hard type of cast iron and ductility is less. The next, malleable cast iron. So malleable cast iron is the product. So as already we have seen in case of ductile cast iron, that whenever we are carrying the annealing process, then ductility increases. Similarly, malleability as well as ductility, these are two properties which are possible due to the annealing process. So malleable cast iron is the product of annealing white cast iron. Already we have seen about the white cast iron that less than 1% silicon is present in white cast iron. So here also in malleable cast iron, same contents is present in whatever present inside the white cast iron. However, annealing process is carried, and that process is carried in between 800 degrees centigrade and 900 degrees centigrade. So 800 to 900 degrees centigrade, up to which the temperature is required to increase for the annealing process, and it is characterized by graphite rosettes. So in case of grey cast iron, it was graphite flakes. Here it is, we are using the word graphite rosettes, malleable cast iron. So malleable cast iron is more ductile than white cast iron. See, as annealing process is carried on white cast iron, in order to get the malleable cast iron, definitely it is more ductile than white cast iron. And carbon is present in between 3% to 4% by weight. Already in case of cast iron, carbon percentage in between 3% to 4.5%, which is same in malleable cast iron also. So coming to non-ferrous metals, here we can see the way of classification of non-ferrous metals. In case of ferrous, we have broadly classified this into the steel and cast iron, and here we are classifying non-ferrous metals as a metals and alloys. Inside the metals, aluminium, copper, cadmium, chromium, cobalt, lead, magnesium, manganese, molybdenum, nickel, platinum, silver, tin, zinc. At the same time, some of the alloys are there which are broadly used in different application areas: brass, which is made from copper and zinc, tin and bronze, copper and tin, aluminum alloys, copper alloys, magnesium alloys, titanium alloys, refractory metals, noble metals, tin lead alloys. So here in non-ferrous metals, basically the content from aluminum to here zinc, in which ferrous is not present, but these non-ferrous metals are having applications, wide application areas. So we will take a brief on the non-ferrous metals, non-ferrous alloys. So non-ferrous alloys vary more widely in their primary metallic constituents and therefore have wide range of properties. Looking to copper alloys, metal based around copper carry significant engineering interest. Copper takes a face-centered cubic. We may consider in short form as FCC, face-centered cubic structure in a pure state. So whenever copper is in pure state, it has FCC structure and is therefore very ductile. Face-centered cubic structure is ductile structure. Copper is an excellent thermal and electrical conductor, as all of we know that our electricity cables inside which copper is present, and at most pure copper have excellent thermal and experimental electrical conductors, and it possesses moderate resistance to corrosion. So copper have strong strength that it possesses resistance to corrosion. The addition of zinc inside the copper is considered to be the alloy called as brass. So copper and zinc will form the brass, which is even more resistant to corrosion because brass have more corrosion resistance and may take either the alpha phase, which is also face-centered cubic and ductile, or beta phase. So beta phase is body-centered cubic and that is harder phase. So see, in brass, alpha phase and beta phase. So alpha phase is face-centered cubic, which is ductile, and beta phase, which is body-centered cubic, which is harder. This is about brass. Then addition of tin inside the copper is called as bronze, and it often contains aluminium, nickel, zinc and or silicon, which is stronger than pure copper. So for bronze, main constituents are copper and tin, and in brass main constituents are copper and zinc. In non-ferrous alloys, again by considering aluminum alloys, aluminum is also the base for many alloys and takes an face-centered cubic structure. So FCC we know that it is ductile, body-centered cubic it is harder. Unalloyed aluminum alloys are remarkably lightweight and aluminum density is 2.7 gram per cubic centimeter. So for aluminum, as we know that it has good resistance to corrosion as well as oxidation due to its self-passivation property. This is very important property, self-passivation property, that it will generate the corrosion resistance layer around it. Aluminum is often strengthened with the addition of alloying metals. So aluminum alloys, if we go the detailed study of the aluminum alloy, then it is also one big domain, but in general we may say that addition of different alloying metals will form the aluminum alloy. Other structural alloys inside that, some less common alloys includes those based from magnesium, which has become popular as a material for bicycle frames due to its extremely low density. So magnesium has extremely low density, 1.7 gram per cubic centimeter. So it is lighter, it is low dense than aluminum also. And rigidity due to its hexagonal closed packed structure. So it has rigidity, it is rigid and low dense. That is very different characteristics of magnesium. Likewise, titanium alloys are more dense than these lightweight alloys. Titanium density is 4.5 gram per cubic centimeter, but it is very strong and have remarkable strength to weight ratio. So titanium alloys, that's why, have applications in aerospace industries, because this is one of the material which is very strong and which have remarkable strength to weight ratios. Then next category of the non-ferrous alloys, inside there is refractory alloys. So whatever we have seen up till now, aluminium, copper, brass, bronze, etc., all these things. So these are having melting temperature less, maybe less than 700 degrees centigrade, near about that. But refractory alloys are the type of alloys which are very strong. It has very strong metallic bond, it has strong elastic modulus, and it has low thermal expansion. It makes exceptionally in high temperature applications. So refractory alloys are useful in high temperature applications. If we take the example tungsten, so it melts at around 3400 degrees centigrade. So one can understand this temperature, because already we are saying that at the sun there is around 6000 degrees centigrade temperature, and tungsten melts at around 3400 degrees centigrade. Tantalum, so there is also one kind of refractory alloy which has melting temperature 3000 degrees centigrade. Molybdenum, it melts around 2600 degrees centigrade. Niobium, so niobium, it melts at around 2400 degrees centigrade. As already we know that all the ferrous metals alloys that melts near about 1500 degrees centigrade, but this refractory alloys which has very high temperature melting point, and that's why these are used at high temperature application. So refractory metals have melting point that exceeds those by steel near about 2 times or more also. Okay, so this is about non-ferrous alloys. Then coming to next category of the non-ferrous alloys, that is super alloys. So nickel, cobalt, iron based alloys are considered to be super alloys that are used in environment that demand extremely low creep and high resistance to oxidations. This is the identity of the super alloys. At temperature exceeds 1000 degrees centigrade, means near about application at gas turbine blades, are single crystal nickel based super alloys blades, and these are coated with the help of zirconia material. The super alloys operates at extremely high temperature and subject to extremely high stress, so exceptional creep resistance. So in aerospace application, maximum super alloys are preferred for the engine parts. Then noble metals. Noble metals are also of interest due to their rarity in nature. So these are very rare, which makes them appealing to jewelers and interest in many chemically reactive environments. The example of noble metals, that is gold, silver, platinum, iridium, osmium, rhenium, and palladium, and they are all resist oxidation. So this is brief about the classification of ferrous as well as non-ferrous alloys. During last lecture we have seen the ferrous alloys, and in this non-ferrous alloys we have seen the copper based alloys, then aluminium alloys, magnesium alloys, titanium alloys, refractory alloys, and super alloys as well as noble metals. So all these non-ferrous alloys and metals have different applications. Thank you for your attention. Thank you very much.